Hey everybody, we're going to cover statistical significance in this video, and we're going to apply it specifically to our t-test that we've been covering in the last couple of videos, if you've been watching in sequence. If not, however, I've decided to make this in such a format that it should be usable for anybody who's just watching this video and wants to learn about statistical significance. So let's get going. Okay, so a quick recap of our scenario. We had two different groups. We had a version of a pamphlet that was green, a version of a pamphlet that was red, and they had different formats or whatever, different presentations, doesn't really matter. Then we tested people on their knowledge of fire safety. Our dependent variable, therefore, was knowledge of fire safety on that quiz, and our independent variable was which pamphlet they read, okay? We obtain a calculated t-value of negative 2.62. Now our next question is, what does that mean? So does that mean that they were roughly the same in their knowledge of fire safety, or was one better than the other? And if so, which one? And how much should we care? Should we start giving people the red pamphlet, the green pamphlet, or does it not matter? Well, that's our question. And what we're essentially getting at here is statistical significance. And so that's what we're going to cover here. So essentially what we're saying is, were they different enough that we can now attribute the differences in their means to the pamphlet that they received? Or were they not different enough that we can say it was due to the pamphlet, it was just because we happen to accidentally find them differently? This is what we're going to cover in much more explicit detail throughout this particular lesson. It's important that we revisit our hypotheses, however. We had a video about this not too long ago, so you can rewatch that as well, but I'll just generally revisit these quickly. So in this sort of scenario, we have two possibilities. The first possibility is that the two groups didn't differ at all. In fact, they didn't differ in any meaningful way. But their knowledge of fire safety was essentially the same, and our pamphlet didn't seem to have any effect whatsoever. That is known as the null hypothesis or the default hypothesis, and it's symbolized in this way. Again, HO equals the mean of group 1 equals the mean of group 2, or HO is the mean of group 1 equals the mean of group 2. So in other words, they didn't differ in their quiz scores. Now, the second possibility, of course, is that they did differ, and there was some impact of the independent variable, the grouping variable, on their quiz scores of fire safety. That is called our alternative hypothesis, and it's symbolized like this, that the means weren't the same, and now we can accept that. So now we need to know which one of these is different, or which one of these is best supported by the evidence. And as we talked about, you generally start off with the default hypothesis. You assume that that is true until you have strong evidence to support the second hypothesis. So what that evidence would be is regarded in the size of the t-value that we obtained. That negative 2.62, we need to know, is that big enough? Is that large enough? Is that a more important enough t-value that we can actually reject our first hypothesis and say that our second hypothesis is best supported? So let's dive a little deeper into what it is that we're doing here now. Let's imagine a scenario where I take a whole bunch of people and I randomly, I just give them this test of fire safety. I just say, hey, everybody take this quiz on fire safety, and they take it. I'll take the same one. And then after that, I say, now, some of you I'm going to call group A. Half of you, you're just group A. Half of you, you're group B. They don't read any different pamphlets. They don't do anything like that. I just randomly call them group A or group B. I shouldn't expect the groups to differ at all in their knowledge of fire safety, right? Because I treated them the same, assuming that I randomly selected them and assigned them to groups A and B. I should expect absolutely no difference in their knowledge of fire safety. Imagine I do that multiple times. I get new samples and I do that again where I just randomly don't treat them I randomly assign them without treating them any differently. What I should see in the numerator is 0 differences, and therefore I would expect, on average, I would get a t-value of 0, because the t-value is an index of the mean differences to the standard deviation, right? And because their mean differences really shouldn't be any different, they shouldn't find any mean differences, that means that I should find 0 most of the time, theoretically. So this is what this is. This is called a t-distribution. A t-distribution is a theoretical distribution of t-values given your sample size if your independent variable had no impact on your dependent variable, like that scenario I just gave. So what's interesting here is we can start to apply other information to this t-distribution to find out where would our meaningful threshold be. In fact, if you recall our lecture on z-scores, in z-scores we learned that 68% of all of the data points in a distribution fall within one standard deviation of that data points of the distribution's mean. Okay, so if we have a mean in t-values of 0, if we should expect most of our t-values hover right around 0, then one standard deviation starts to get a little bit rare, right? We start to say, wow, these are unusual t-values if they're one standard deviation beyond. However, to jump ahead a little bit and take this to its logical conclusion, we find this, that 95% of all t-values obtained in this way should fall within 2 standard deviations of the mean. Now, what's interesting there is that means if they fall outside of those 95%, they're unusual t-values. We wouldn't expect those t-values to occur unless there is an impact of the independent variable on the dependent variable. Okay, that's essentially what we're going for here. So what we find is in these tails of the distribution is what we call those tails of those distributions. If we split the 5% out, we get 2.5% negative values this far away from 0, and 2.5% of positive values this far away from 0, 2 standard deviations above 0. Those are unusual t-values to have occurred if we didn't have an impact of the independent variable on the dependent variable. Therefore, if we find one of these t-values, we can sort of safely say we probably didn't get this t-value by accident. We probably didn't just happen to find one of these rare t-values. We probably got this t-value because our grouping variable did influence the scores on our dependent variable. That's essentially what we're getting at. Another way that you can think about this is that t-values that fall outside of those 2 standard deviations from the mean are interesting. That means that we probably had an effect of our independent variable on our dependent variable. At least it's strong enough evidence to state that we probably did. And then any t-values that you find in between, in other words, within those 2 standard deviations of the mean of 0, probably are not interesting enough. Maybe there is something going on, but we just weren't able to say so. And so because we're not able to say so, we default to our null hypothesis, which says our independent variable did not influence our dependent variable. Okay. All of this has to do with something called statistical significance. That is exactly what this is. Statistical significance is how unusual is your statistic that you found given the characteristics of your sample. In other words, if your independent variable didn't do anything to your dependent variable, how likely is it that you still found this statistic? That then is what we use to decide whether we had statistical significance or a meaningful t-value, or essentially one of our groups was different from the other group, and which of the null or alternative hypotheses we accept or we support. We symbolize statistical significance with a lowercase italicized letter p. Now, that's maybe not very helpful, but if you think of it as standing for sort of the probability that you found this statistic, even if your independent variable didn't have an impact on your dependent variable, that will be helpful. Now, that is a loaded sentence, I understand, and you're going to probably have to think about that, sort of memorize this bold sentence here, I think, will be very helpful, and think about this a lot. Some people it takes years to kind of finally for it to click, but that's essentially it. So the sort of counterintuitive thing here is that what that means is you want a probability of having found this by accident to be very low. You want a very low probability that this t-value just occurred, even if there's no impact of the independent variable on the dependent variable. Now, to translate that into more usable terms, what that essentially means is you're not interested in any p-values that are 5% or less. In other words, you're looking for statistics that occur less than, well, I should say 5% or less of the time in order to say that there was an impact of the independent variable on the dependent variable. Again, this is fairly complex, so feel free to review this, go over this multiple times, put it on repeat, that's fine, and work with that. So in practical sense, what we're looking for is if p, the lowercase italicized p, equals 0.05 or less, that is statistically significant, and the null hypothesis can now be rejected, and you can sort of state with confidence that the independent variable had an impact on your dependent variable. Now, it doesn't prove anything necessarily, because there's more to it. You got to make sure that you're ruling out other plausible alternative explanations, you're replicating your findings and things like that, opening it up to peer review and all that kind of stuff. But you can now say that you have some evidence that the independent variable made a difference in your dependent variable. Okay. So then back to our question, we obtained a t-value of negative 2.62. What do we do with that? What does that mean? What is our threshold? Did this exceed our threshold for statistical significance or not? Unfortunately, there is no threshold that is just universal to t-tests. It actually changes depending on the size of your samples, because it turns out that as you have smaller samples, that means that the size of the t-value is much easier to have larger, even if it's not statistically rare, I'll say. And so the threshold size is going to change depending on the sample size. So luckily, we don't have to actually do any calculations here. We already have everything we need. We are going to have to learn how to read a graph or a table, however. I'm going to show you a table in the next video so that we can kind of see how to read one of these tables to determine what should the threshold be for a test with my sample size. Okay, that's not going to be very difficult, but I'll show you how to do that next, and I will see you then. Thank you very much.